Let's work on rederiving Euler's equations for precession. So we learned way back in chapter 3 of Taylor's book that the rate of change of angular momentum is the vector sum of external torques. Let's just say one torque. External torque. But this was expressed in an inertial frame. It was expressed in a frame whose axes are fixed in inertial space. So we'll call this the space axes. Meanwhile, we saw last week that it is that many expressions for the angular momentum and the kinetic energy are much simpler when expressed in the body axes rather than the space axes, because in that basis the inertia tensor is diagonal. So meanwhile, we can go back to a result from John Taylor's chapter 9, which is that for any vector q, we can relate the time derivative of that vector q so it's the same vector q, but we can observe it from a set of axes. We can project that vector onto a set of axes fixed in space, or we can project that vector onto a set of axes that are rotating in space, maybe co-rotating with some body, and the components of that vector have a different time dependence depending on whether we are projecting the vector onto the set of axes fixed in space or the set of axes co-rotating with some body. So in chapter 9, that was some arbitrary vector q. Let's just do that for the special case of the vector L, the angular momentum vector. So we have dl by dt in the space axes equals dl by dt projected onto the body axes plus omega cross L. Okay, so now we can just combine these two results and we'll say the external torque equals dl by dt in the body axes plus omega cross L. Okay, so now we know that L has a simple expression in the body axes. In other words, the axes E1, E2, E3, that are the principal axes of the inertia tensor. So in particular, let's see, so this is, so the components here of L are L1, L2, L3, and then it's just L1 dot, L2 dot, L3 dot. So, for instance, the three components here are, so this is L1 dot, so it's omega 1 dot times lambda 1, and omega 2 dot times lambda 2, and omega 3 dot times lambda 3. So that's dl by dt in the body axes. And then we have the omega vector, so that's omega 1, omega 2, omega 3, cross product with the angular momentum vector. So that's L1, omega 1, lambda 1, omega 1, lambda 2, omega 2, lambda 3, omega 3. So this is one moment of inertia, one moment of the inertia, one eigenvalue of the inertia tensor times the corresponding component of the rotation vector, and then moment eigenvalue 2 of the inertia tensor. So that's the moment of inertia about axis number 2, principal axis number 2 times omega 2, and so on. Angular momentum, moment of inertia about principal axis number 3 times omega 3. Okay. So, and meanwhile, this is going to equal this vector gamma 1, gamma 2, gamma 3. So this is the torque vector. Now, normally you think about the torque vector in terms of x, y, z components in space, but we can project it at any instant onto the 1, 2, 3 principal components. And now we can try to write out components of this result. So let's start with number 3. 3 is usually my favorite. So let's say gamma 3 equals lambda 3 omega 3 dot plus, now we want the 3 component of this omega cross L vector. We want the 3 component. And we can just remind you that if we have, let's say, a cross product, where am I going to write this? If we have a cross product A cross B, and we want the 3 component, then that's A1 B2 minus A2 B1, and then we can just use cyclic permutation. So the 1 component, so you add 1 to everything. 3 becomes 1, 1 becomes 2, 2 becomes 3, 2 becomes 3, 1 becomes 2, and so on. So we'll see that in just a second. So this is, okay, lambda 3, omega 3 dot, plus, so now we have, this is the 3, so we want the 1 component of this, omega 1, and then we want the 2 component of this, so that's omega 2 lambda 2, and now minus, and then we want the 2 component of this, so here's omega 2, we want the 1 component of this, so that's omega 1 lambda 1, so that equals, so we have, actually we can, while we're at it, we can pull this over to the left side because you kind of make a nicer looking result. So we'll get lambda 3 omega 3 dot equals gamma 3. And then we have, okay, so now this is a minus sign, so it'll become a plus sign. So there's on the other side of the equation, omega 1, omega 2, lambda 1, minus omega 1, omega 2, lambda 2. And in fact, let's group here. So we'll say lambda 3 omega 3 dot equals gamma 3 plus lambda 1 minus lambda 2 omega 1 omega 2. Okay, now we can just use cyclic permutation of the same result. So 3 becomes 1, lambda 1 omega 1 dot equals gamma 1 plus 1 becomes 2, lambda 2 minus 2 becomes 3, lambda 3, then we'll say omega 2, omega 3, and we can say lambda 2, omega 2 dot is gamma 2 plus, so here's lambda 3 minus lambda 1, omega 3, omega 1. So this set of 3 equations is called the Euler Equations. Euler has his name on so many different things. So these are the Euler Equations for precession of a rigid body. And one particularly interesting case is that in which the external torque is 0, and so then we can just eliminate these 3 gamma terms. So we're going to talk about that in just a moment on basically the next mini lecture here. Okay, one other thing. Professor Liu was pointing out last week that all of this stuff is written in terms of 1s, 2s, and 3s because that's very convenient for working in the basis in which the inertia tensor is diagonal. The expressions for angular momentum and kinetic energy are much simpler in that basis. But usually in real life, you have the torque expressed in x, y, z components. You have to, at a given instant, take the torque in the x, y, z basis and project it into the 1, 2, 3 basis in order to use this result. Okay, so now I think let me just write down what we're going to use as a starting place for the next point, which is we're going to say, okay, if the torque is 0, then we have omega 3 dot equals lambda 1 minus lambda 2 over lambda 3, omega 1, omega 2, and we have omega 1 dot equals lambda 2 minus lambda 3 over lambda 1, omega 2, omega 3, and lambda omega 2 dot is lambda 3 minus lambda 1 over lambda 2, omega 3, omega 1. Okay, so we will make use of this result to do some kind of fun applications in the next segment.